Here's a handy lemma. Let C and D be subsets of a topological space X. Assume that C is connected and is contained in D. And further assume that U and V form a separation of D. Okay, so I've sort of split D into two different parts. Well, then either C has to be in U or C has to be in V. Okay. The reason is if C was not completely in one or the other, then it would intersect both of them. And you could take the intersection of U with C and the intersection of V with C, and that would give you a separation of C. But we know that can't exist because C is connected. All right, so connected subsets have to end up inside of one half of the separation of a larger set. Okay, theorem 6.9, we're about to prove something similar to this, so let's take a look at it. Let X be a topological space. Let C sub alpha be a collection of connected subsets of X, such that the intersection of all of them is non-empty, which means that the entire collection has at least one point in common. Okay. Well, then the union is connected. So here's an illustration. I've just taken an index set A to have sort of 4 numbers in it, so we have a collection of 4 connected subsets of X. So each one of them individually is connected, and moreover, they all overlap at, in this case, just one point. It could be a much larger intersection if desired. And you end up with a connected subset when you take the union of all 4. Right? Okay, so that's another nice theorem for proving things are connected. Now, our problem, 6.8, says let X be topological space, and suppose we, again, have a collection of connected subsets of X, but we are restricting our index set to be a set of positive integers. Okay, so you basically have a sequence of connected subsets of X, and we're not assuming that they all overlap, right? That there's a point in every single one of them. We're just assuming that consecutive subsets in our sequence do overlap. Okay, so here's a picture. A1 has a non-empty intersection with A2. A2 has a non-empty intersection with A3. Okay, but it may be that A1 and A3 have an empty intersection. That's all right. So in some sense, compared to theorem 6.9, this statement's a bit weaker because we're only talking about an index set Z+, but our hypotheses are also weaker, right? We're assuming a little bit less. Okay, so it's not just a direct application of theorem 6.9. We don't have this assumption. Okay. All right, well, we need to prove that the union of this entire sequence of subsets is connected. Okay, well, my first thought when I sort of looked at this theorem and this exercise next to one another was just to use induction, right? Sort of use theorem 6.9 a bunch of times, just applying it to these pairs of consecutive subsets and to get that the whole union to be connected that way. But it doesn't work, right? Let's look at it and sort of think about why it doesn't work. So here's the invalid proof. Right? We use induction. For the base step, we just have that the union of the first one, which is just A1 itself, is connected, and then that's given. Right? We're assuming that each of these individually are connected subsets of X. And then for the inductive step, suppose that you know that the union of the first n are connected. And then I want to show that if I add on one more, that's connected as well. Okay, and so I can apply theorem 6.9 because just to a pair of sets, right? The first set being A1 union through AN, and the second set being AN plus 1. It's true that the intersection of these two is non-empty because I know that there's a point in AN and in AN plus 1. Okay, so if I make this first thing bigger, it still overlaps AN plus 1 somewhere. So I do have the hypothesis for my theorem, and so I can conclude that the union of these two sets, the one in parentheses and AN plus 1, is connected in X. All right, actually, the proof that I have so far there is completely valid. And the problem is it doesn't lead to the result that I want, right? What I've shown is that for any n, a1 union dot 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 union an is connected. Okay, I've shown that any sort of collection of finitely many of these subsets in my sequence is connected. I haven't shown that the entire infinite union of these subsets is connected. Okay, so there's a distinction there. I've shown that you can go as far as you want in taking the union of these subsets, and that'll be connected. But we don't know that you can sort of take all of them at once, right? Okay, so we need to do something a little bit different to obtain that. So we need to get down to the definition of connected a little bit. So here's the proof that it's actually going to work. Suppose U and V form a separation of the union of all of these A sub j's in X. Okay. Well then, by lemma 6.7, which was the first one we talked about up here, since we're assuming A sub 1 is connected, it has to be contained in one of these two subsets that form a separation of this larger space containing A1. Okay, so whichever one it's in, let's call that one U. We can rename them if we have to. And I'm going to prove by induction that actually every single one of the A sub j's is in U. Okay, and this is going to give me what I want, because I do know that if each A sub j is in U, then the infinite union of A sub j's is also in U. Okay, so that's how I'm going to get from sort of finite union, or to an infinite union level. All right, so how does this go? Well, we have the base step right here already, that A1 is in U, and so now we're going to assume that any AN is a subset of U. And okay, well, we know that AN and AN plus 1 have a non-empty intersection. Okay, so since that's true, there exists some point X in the intersection of these two sets. Yep. And, well, if it's in AN and AN plus 1, if it's in AN, it's in U as well, right? So we actually have that this point is in U intersect AN plus 1. Okay. Well, if AN plus 1 intersects U, remember that AN plus 1 is connected, right? So again, by theorem 6.7, we know that AN plus 1 is contained either in U or in V. Now, if it were contained in V, remember U and V form a separation, so they're disjoint. So then it couldn't intersect U, right? If AN plus 1 were contained in V, U is disjoint from V, so it could not intersect U. Okay, but it does. The only other possibility is that A sub n plus 1 is actually a subset of U. Okay. Let me write a little bit of that down here. This implies that A sub n plus 1 is not a subset of V. Okay. Thus, by lemma 6.7, A sub n plus 1 is a subset of U. All right, and that's what I needed to show to get to finish off my proof by induction. So my conclusion then is that every A sub j is in U, and therefore the union of the A sub j's is in U. Okay, we conclude that the union of the entire sequence of A sub j's is a subset of U, right? And if that's the case, then what do we know about V, right? Remember, the union, U and V formed a separation of exactly this union here, right? So U union V equals this thing, and U and V were disjoint, but okay, this is saying that these two sets are already equal, right? That means V has to be the empty set. Okay. U already takes up the whole union. If they're disjoint, V has to be empty. And that's not allowed for a separation, right? This contradicts the assumption that U and V form a separation of this union in the topology inherited from X. All right. Therefore, we know that our union is connected. Okay, we assumed we had a separation of the union and we got a contradiction. Therefore, there isn't any separation and it must be a connected set.